Why do castles crumble, stars burn out, and ice melt into water? Why does your coffee always go cold, but never spontaneously heat back up? The answer lies in one of the most profound and universal principles in physics: entropy. Entropy is a measure of disorder, or more precisely, the number of possible ways a system can be arranged. The more disordered the system, the higher its entropy. And according to the second law of thermodynamics, in any closed system, entropy can only stay the same or increase. This single principle underpins the direction of time, the evolution of the universe, and even the eventual fate of everything that exists. So, what exactly is entropy? Imagine a neatly stacked deck of cards. That's low entropy. There's only one way to arrange the deck so every card is in order. Now shuffle it. There are trillions of ways the deck could be scrambled, and each one is a higher entropy state. The same logic applies to atoms, molecules, and even galaxies. Entropy explains why heat flows from hot to cold, not the other way around. It's why gases spread out in a room instead of clustering in a corner, and why stars eventually run out of fuel. It's not that these processes are forbidden in reverse. They're just so incredibly unlikely. The number of high-entropy configurations vastly outnumbers the low-entropy ones. So statistically, the universe moves from order to disorder. Entropy and the arrow of time. Entropy gives time its direction, while the laws of physics are time-symmetric. They work the same forwards and backwards. Entropy introduces a distinction. The past is more ordered. The future is more chaotic. You remember yesterday because your brain formed memories in a lower entropy state. You don't remember tomorrow because it hasn't happened, and because entropy hasn't increased there yet. So in a very real sense, entropy is what makes time feel real. Without it, there would be no irreversible processes, no aging, no causality, and maybe no consciousness. Entropy and the early universe. The early universe was hot, dense, and surprisingly so ordered. This is strange, because high temperature usually means high entropy, but the early universe had extremely low gravitational entropy. Matter was spread out smoothly, like a calm pond. Over time, as gravity pulled matter into clumps, stars, galaxies, planets, entropy increased. That's why the universe can create structure. Even as it increases in entropy, local pockets of order, like life, can form as long as the overall entropy goes up. This is key. Entropy doesn't forbid complexity. In fact, it enables it. Entropy and life. You are an entropy machine. Your body takes in low-entropy energy, food, sunlight, oxygen, and converts it into motion, thought, heat. Along the way, you produce high-entropy waste, carbon dioxide, body heat, disorder. Life doesn't violate the second law. It runs on it. We maintain internal order by increasing entropy in our surroundings. Even your brain, with its thoughts, memories, and dreams, is powered by entropy flow. Some researchers believe consciousness itself may depend on entropy gradients, the flow of information through complex networks, the entropy and the end of everything. As the universe expands, entropy increases. Eventually, stars will burn out, black holes will evaporate, and matter will decay. What's left is a cold, dark, high-entropy cosmos, the so-called heat death. In this state, everything is maximally disordered. No more energy flows, no more processes, just a vast, silent equilibrium. In this future, time loses meaning. Without change, there is no before or after, only endless stillness. This is the ultimate consequence of entropy, a universe that winds down like a cosmic clock, ticking towards silence. Can entropy be reversed? Though, in theory, entropy can course decrease, but only with an input of energy and effort. A refrigerator, for example, reduces entropy inside by increasing it outside. Life does the same. But globally, entropy always increases. Some speculative ideas in physics, like entropy reversal after the Big Crunch, or Boltzmann brains, arising spontaneously in high-entropy vacuums, suggest that order can emerge even from chaos, albeit rarely and strangely. In the far future, new low-entropy regions might bubble into existence, perhaps even new universes. Entropy and information. In recent years, scientists have linked entropy with information. In fact, the formula for entropy in information theory is almost identical to the one in thermodynamics. This has led to radical ideas that the universe is not just made of matter and energy, but information. And entropy is a measure of missing information. Black holes, for example, have entropy proportional to their surface area, not volume. And Hawking radiation, which causes them to evaporate, is deeply tied to information theory. Could the universe itself be a giant or information processor, evolving through entropy? The beauty of entropy. At first glance, entropy seems sad, the slow march toward chaos. But it's also the reason we exist. Without entropy, there would be no change, no motion, no heat, no stars, no life. It is entropy that fuels evolution, drives creativity, and gives time its flow. Without it, the universe would be static, silent, and sterile. At Infinity Beyond, we don't fear entropy, we celebrate it. Because it means the universe is alive, moving, breathing, changing. And in the increasing entropy of the cosmos, we find meaning, fleeting, fragile, but magnificent. In our next episode, we'll ask a different kind of question. Could the universe itself be alive? What does it mean for a cosmos to be conscious, self-organizing, or even self-aware? Subscribe now to Infinity Beyond, and let's continue following the trail of entropy into evolution, emergence, and beyond.